Our page table examples used in illustrations so far have been for tiny processes with only a handful of number of pages. Real processes are significantly much larger, hence their page tables may include more entries, hundreds or even thousands. So let's look at some potential issues with handling huge page tables. Let's refresh your memory about page table. So we know that each process will be associated with one page table, and the number of entries in the page table of that process is proportional to the process size. But there's a limit. The maximum number of entries in the page table is determined by either the maximum size of the logical address space and also by the page size selected by the hardware. So as you increase the page size, that means the number of pages will go down. But if you decrease the page size, then you will see more pages. So page table must be stored in RAM and they have to be stored contiguously. It will be an issue when the page table is much bigger than the size of a single page, because that means the page table may not be contiguous. At this point, you should view page tables like data structure used by the operating system to store relevant information about the pages owned by a process. Besides storing the frame numbers needed for address translation by MMU, each entry in the page table stores other information such as memory protection, access mode, frequency of references, and other flags. For our discussion, we will assume that all this information can be packed into a 4-byte data structure. We also assume the architecture used 20-bit logical address. Compared to today's CPU, 20-bit address is on a very low side. Many 32-bit CPUs provide 32-bit logical address space, which gives you a maximum of 4 gigabytes. So remember, 4 gig is 2 to the power of 32. So the table on this page shows you the effect of fixing the page size to the maximum size of page table of each process. So again, we assume 20-bit of logical address and each page table entry is a 4-byte data. So let's look at different options. So if the page size is 8K, and remember 8K is equivalent to 2 to the power of 13, that means the number of bits in the offset is 13 bits because of that number. But because the total address space is 20-bit, then once you take out 13 for the offset, then there are only like 7 bits for the page number. So the total number has to be 20. With page number allocated as a 7-bit number, that means we can have at most 2 to the power of 7 pages. Now combining the information from earlier, because now each page entry requires 4 bytes data, if you have 2 to the power of 7 pages, that means the page table size would be 4 times 2 to the power of 7. So 4 is 2 to the power of 2, and then 2 to the power of 7. If you multiply the 2 together, and you will see 2 to the power of 9. So now for this example, for this case, the maximum size of your page table will be 512 bytes. Now, if you look at the page size, so the page size is 8K, and the page table, the maximum size of the page table is only 512. This number is much smaller than the page size. So that means for a page table of size 512, it will fit perfectly inside a single page. Look at the second example. When the page size is smaller, we change to 4K, and then remember 4K is 2 to the power of 12. Once 12 bits are allocated for the offset, that means the number of bits for the page number is only 8, and with 8 bit of page number, you will get the maximum of 2 to the power of 8 pages. And if each entry requires 4 bytes, again we do the same math, and from here we can see the maximum size of your page table can be as high as 1K. But with page size of 4K, 1K is still smaller than a single page, so we don't see any problem. And then same thing for 2K, so the same analysis with 2K of page size, that means the offset requires 11 bits. That means the bits for the page number is 9 bits, and with 9 bits we're gonna have maximum of 2 to the power of 9 pages. And then from there we can calculate the total size of our page table would be 2 to the power of 9 multiplied by 4, and you will get 2 to the power of 11, which is equivalent to 2K. And this is an example where the maximum size of a page table will fit exactly into a single page. But as you decrease the page size, then the number of pages will be higher. So in this case, with pages of 1K, and 1K is 2 to the power of 10, because 10 bits has been given to the offset, with a 20-bit address, we have only 10 bits for the page number. 10-bit page number will give you a maximum number of pages 2 to the power of 10, and if each page entry requires 4 bytes, then the total size of your page table can be as high as 4K. And this is a problem because your page is only 1K and your page table may be as big as 4K, which means your page table will not fit into a single page. So your page table may span across 4 different frames. So this would be an issue because in order for the memory hardware to work, the page table must be contiguous. So when the page table span across multiple frames, there's no guarantee that the page tables will be contiguous. So how do we solve this problem? There are 3 options to solving this problem. So the first technique is hierarchical paging, and the second is hashed page tables, and the third is inverted page table. So the motivation behind using hierarchical paging is essentially adding another level of indirection. So let's use an analogy of printing a list of ATM machine locations for a particular bank across the US. So let's assume that your bank has a total of 1,000 ATMs across 50 states in the US. That means we have an average of 20 ATMs per state. If you include a table of contents for this document, the output and the table of content, or you can think the table of content as a directory listing of all the ATMs, will certainly span across several pages of printout. Alternatively, you can organize the ATM locations by states and then rearrange the table of content into 2 levels. Using a hierarchical list, the top level table of content shows the list of only the names of 50 states. Certainly, list of 50 states will fit into a single page of paper. And the low level table of contents show a list of ATM locations within a given state. And in here, in my example, you will see there will be 1 page for all the ATMs in Alabama, and then another page for all the ATMs in Alaska, and so on and so forth. So if you compare the 2 approaches, using a linear list, let's say the total number of pages to print the ATM locations require 50 pages of paper. So using a linear list, you will need only to use 50 pages of paper. But with hierarchical lists, because we have to keep the top level table of contents, that means we need a sheet of paper to print the top level table of contents. So what is the benefit of this approach? The list of ATMs within a state will certainly fit into a single page. So although the overall data span across multiple pages, but using this trick of indirection, then we will see the list of states as a contiguous list inside the main table of content or the top level table of content, and then the list of ATMs within individual states is also contiguous. So let's look at the implementation in MMU hardware. So I'm using a different abbreviation here. Instead of MMU for Memory Management Unit, sometimes we're gonna call it Memory Control Unit. So in our diagram, we're gonna assume that each frame in your RAM is a 4K byte frame, and we're gonna assume again 4 bytes of page table entries. That means we can see on each page we can store up to 1024 page table entries. The page table based register stores the address of the outer page table. The outer page table is shown in a lighter shade of green. Each entry in the outer page table stores the frame number or address of one of the inner page tables. This outer page table is similar to the idea of top level table of content containing the list of states in the ATM location analogy. Each of the inner page tables, shown in darker shade of green, holds the frame number where your data or instruction can be found. So we assume a page size of 4K. So everything here is 4K. So the page tables are 4K, and then the block that you use to store your data or instruction are also 4K. And remember, 4K is 2 to the power of 12. So it is important to understand that this diagram is drawn to scale. So the same size of box or the same size of rectangle that you see here is to represent a block of size 4K. So this is 4K, this is 4K, and these blocks are also 4K. So using this example, the outer page table can hold up to 1024 rows, and each row points to another lower level table which can also hold 1024 entries. So then combining the two together, that means we're gonna see in here in the darker shade of green boxes, we can see up to 1 million, or exactly 1024 times 1024, or 1 meg of frame numbers. This is similar to the idea of ATM locations that we used earlier. The top level table of content can hold the location of 50 different states. Each row in here will point to a page that can hold up to 20 different ATM locations. So that's why the total is 50 times 20, and altogether we're gonna see 1000 addresses. So how does this affect the format of our logical address? With one level paging, the logical address has only two parts, the page number and the offset. With two level paging, then the logical address is now a triplet. The first number of the triplet is an index into the outer page table, and then the second number in the triplet is an index into the low-level page table, and then the third number in the triplet is the offset of data or instruction into these pages. So because we have 1024 entries in the outer page table, that means the number of bits for P1 will be 10 bits. And then same thing because we have 1024 entries in the next level page table, so the number of bits in P2 is also 10 bits. And the offset refers to every byte in your data or instruction. So that means the number of bits for the offset has to be 12 bits because 2 to the power of 12 is 4K. So we have 10 bits in here, 10 bits for the inner page table number, and then 12 bits for the offset. So total we have 10 plus 12, which is 32. So you learn the overhead of paging. For every memory referenced by the CPU, the MMU will make 2 memory references. Now with 2-level paging, then the MMU will make 3 memory references. The first 2 references are to look up into the outer page table and the inner page table. The third memory reference is to fetch the actual data or instruction. So let's look at some numerical example. So now let's say the logical address is a triplet of 17, 72, and 830. And remember, this number is a 10-bit number, that number is also a 10-bit number, and this number is a 12-bit number. So 17 is the index for the outer page table. So in our example, row index 17 has this value of 50, and 50 tells us that the next inner page table will be at frame 50. So then the MMU will fetch frame 50, and this is the inner page table, and then number 72 will be used as the index into the inner page table. So in our example, if we see number 641, that number tells us that the data or instruction referred to by this logical address is actually found in frame number 641. So the MMU will fetch frame 641, and then the offset 830 will be used to fetch one instruction or data from frame 641. So let's inspect the logical address format in more details. So we are using the same example as before, and I just want to show you how the numbers are encoded in binary. So the outer page table index is 17, and 17 in 10-bit binary is 00001, 0001. And the inner page table number is 72, and that number in 10-bit binary is shown here. And then the offset 830 is now a 12-bit number, and then that number in 12-bit binary is shown here. Combining the 3 numbers as binary, this is what you get. So the binary representation of 17, then the binary representation of 72, and then the binary representation of 830. Before we can convert this number to hex, again, we have to group the binary numbers in group of 4, starting from the rightmost position. So here I have only 2 binary numbers. If I want to group them, I need to use the 01 from the outer page number and then bring those 2 bits together with the 00 from here. So after regrouping the binary bits in group of 4, now this is what I get. So the first group of 4 is a 0 in hex, The next group of 4 is a 4 in hex, and so on and so forth. Now in hex, that logical address is actually 0444833D. Let's now look at examples of real CPUs that use hierarchical paging. We will look at Intel and AMD CPUs. On a 64-bit CPU, theoretically, you can have up to 16 exabytes of logical space. In decimal, this value is close to 1 quintillion, which is 10 to the power of 18. However, most CPUs in production currently support 48-bit logical address space. How does this CPU design affect the internal OS data structures? With more bits to store in the address, the page table entries do not fit into 4 bytes anymore. So the page table entries expand from 4 bytes to 8 bytes. But also larger entries implies fewer of them can fit into a single memory frame. But also fewer entries implies fewer number of bits will be assigned for a page number. And to cover 48 bits address, using fewer bits of page number, the logical address format must use deeper hierarchy, up to 4 level deep. The family of 64-bit CPUs by Intel or AMD support several address formats. Page sizes range from 4K, 12 bits offset, to 1 gig, 20-bit offset. These CPUs can access a physical RAM up to 4 petabytes. So Intel or AMD 64-bit CPUs can run in either 32-bit mode or 64-bit mode. When running in 64-bit mode, most of these CPUs support up to 48-bit logical address. In 32-bit mode, the CPUs can be configured to use 1 out of 4 address formats. The first format is actually the 2-level paging example that we saw earlier. The logical address is a triplet of 10-bit page directory, 10-bit page table, and 12-bit offset. So this is what we note as the outer page number and is the inner page number. The second format uses a 1-level paging with the higher 10 bits for page number, or Intel call it page directory, and the lower 22 bits for offset. The page size used by this format is 2 to the power of 22, which is 4 meg. The third and fourth formats use leading 2 bits as an index to a small table called PDP, or Page Directory Pointer. In 64-bit mode, all the page number use 9-bit values, so 9-bit values everywhere. And smaller page sizes are compensated by deeper hierarchical levels. So when the page size is 4K, the page format has to use 4-level hierarchy. With bigger page size, the address format uses like a 3-level hierarchy. Recall that the page numbers are used as an index to the outer, inner, or sub-sub page tables. Therefore, for easier hardware design, each address format uses the same number of bits for page number. This is why you see either 9 bits or 10 bits used several times in one format. So this is an example where the address format uses 9-bit everywhere, and this is where 10 bits shows up twice. Let's now look at the second technique of handling large page tables, hash tables. The motivation behind using hash page tables is that not all entries of a page table are used, especially when demand paging is used by the hardware, in which case only pages referenced by your program will show up in the page table. So why waste the space into the page tables when the tables themselves are sparse. Another reason for not using hierarchical paging is extra memory reference by the MMU hardware. Deeper hierarchy requires more memory reference. For instance, 4-level paging requires a total of 5 references for each logical address issued by the CPU. But we also know the high-speed cache will help to decrease the overall memory access time. So this is why replacing a linear array with a hash table makes sense. Implementation of a hash table requires a hash function. Recall from your data structure course that the purpose of the hash function is to convert content to index into the hash table. In our case, the content is the page number, and we do want to convert the page number into an index into this array. But as you remember from your data structure, hash tables may encounter data collision where two different contents yield the same index. There are several techniques for collision handling. The one shown here is separate chaining, where collided keys are maintained into one linked list originating from the same entry in the hash table. The hash table essentially maps page numbers to frame numbers. Using a hash table, the MMU will perform the address translation using the same approach that you learned earlier. So the incoming logical address as a pair of page number and offset will be used to do a lookup into the hash table. So the page number will be converted into an index using the hash function, and then a matching frame number, page number will be searched inside the hash table. And then whenever there's a match, then the frame number corresponding to the incoming page table will be used to generate the physical address. So now we look at the third technique for handling huge page tables. Essentially, page tables are used for mapping page numbers to frame numbers. And so far, we have seen using the page number as either an index into a regular page table or a key into a hash page table. In both techniques, the page number is considered as input and the frame number as output. With inverted page table, we reverse the roles of input and output. Now we treat frame numbers as input and page numbers as output. So the inverted page table essentially maps frame numbers into page numbers. Another benefit of this technique is that per process page table are eliminated and replaced with one global inverted map. This illustration shows two processes, red and green, with 5 and 3 pages in their logical space. The page table of each process is intentionally shown, but they are crossed out just to remind you that they are not used anymore. In place of per process page table, the system now maintains a global one copy inverted table whose size is proportional to the number of physical frames in your RAM. So in our example, we have 10 frames in our RAM, and the size of the global inverted page table is 10 rows. Each row of the inverted page table holds the page number of the process using a particular frame. For instance, the first frame, frame 0, is allocated to page 2 of the red process. So that's why you see here number 2, because this is like page 2 of the red process, and the PID of the red process will be included in that row. The second frame, frame 1, is allocated to page 2 of green. So page 2 of green. We have to include the PID of the owner into the inverted page table in case we have two entries with the same page number, the same logical page number. So this is how we tell that frame 0 is owned by red and frame 1 is owned by green. This illustration shows an example when the red process attempts to fetch instruction or data at logical page 1 and offset 8A4. For searching the inverted page table, the logical address is tagged with the PID of the red process, and then the pair of PID and the page number is searched for a matching entry in the inverted page table. In our example, a matching entry is found at index 4. Red PID, page number 1, matching entry at index 4. This tells us that this logical address from red can be found in frame 4 in your RAM.